Our project came from Dr. Alex Awning of Virginia Tech, who's originally from Ghana. Since the infrastructure in Ghana is not too well and the power comes in and out, he would like to create a solar-powered charger for cell phones, so people in the areas where they don't get power all the time will be able to use cell phones and other technological advances that we've had in the past few years. So our project right here was to really design a solar-powered cell phone charger that was portable and was able to be slightly reliable, whatnot, so it can handle the hot heats and humidities of cell phone charging, like the solar and being out in Africa in the intense heat. So first off, our main project was that we have to design something that can handle the entire power of a cell phone, to charge an entire cell phone. So we decided to go with a 10-watt solar panel, so it could easily charge the full USB 3.0 output power of about 5 watts, including any losses that you'd possibly have in the circuitry, as well as any housekeeping power needed for like the microprocessor and whatnot. So in order to optimize the output of the power output of the solar panel, we implemented maximum power point tracking from the right here in the buck converter. So what that would do is that the way solar panels work is not a perfect output. Depending about the amount of light that's hitting a solar panel, the power is actually slightly varies in the voltage and current levels. So this kind of algorithm here works by adjusting the output power slightly and seeing does it change, like the output voltage, and measuring the current, and then it sees does it change the power level, does it increase or decrease, and it tries to find that perfect point for the maximum amount of power delivering. So it's always delivering the most power it could possibly handle. In order to take full advantage of this maximum power point tracking, we put in a middle stage of a nickel metal hydride battery that we charge using a simple change in voltage measurement. So we'd be constantly just dumping as much power we can into that device and just measuring the output voltage. And we notice the output voltage reaches peak and then starts to drop. We know the battery's at a full charge, so we stop charging it there. So this allows our microprocessor to be able to handle both delivering the maximum power from the solar panel as well as preserving the AA batteries, which the nickel metal hydrides are just a simple AA Duracell batteries. So this allows us to really handle everything. It just does all that kind of work. And that was from a Texas Instruments chip we used. We used the MPS 430 F1232, which was actually wasn't really a power electronics kind of like microprocessor controller, but the reason why we picked it was because it consumed very minimal power, especially in standby power. It consumed like less than a watt. Since ideally we'd like to use the charge in those batteries to charge the phone and not charge all the housekeeping electronics. So let's say if we put the panel out away from the sun for a while, it doesn't consume all the energy and just turn off and not work anymore. From that battery, we then need to step the voltage up out to a USB output power. The reason why we selected using USB 3.0 power is that all cell phones these days are really starting to standardize to this power level. This power level, so this would allow us to charge any type of phone you want, from your smartphones to your dumb phones to anything, really, as well as any other electronic devices too. So you could charge MP3 players or just any kind of electronic device that anyone might want to use. So in order to step that voltage up from the whatever voltage the battery's at, from about 3.3 to 4.2 volts up to the 5 volts needed, we just needed to use a simple boost converter. And we were able to implement that using the Texas Instruments TPS 2500, which was great because it was a nice small package, highly efficient, and it was a simple, very small, and just no problems at all. So it's nice, easy design. We were able to focus more on the just digital control of the MPPT and the battery management. This thing also allowed us to prevent over discharging the batteries too, because it had kind of under voltage, over voltage lockout, mostly under voltage we cared. So we designed it so as soon as the batteries dropped to the minimum voltage we want, we could just tell it turn off. And then from there, it would just shut off. We could have it, originally our design was to have an LED turn on to say, this doesn't work anywhere, like you're done, and then so you know that it's done discharging, and then you can go put it back in the sun, to start charging the battery again.